On November 28, 1938, legendary aviator Charles Lindbergh sat down to write a letter to his colleague Joseph Ames. Lindbergh had been visiting Germany regularly for several years during a period of aeronautical achievements such as the Hindenburg airship, the first supersonic wind tunnel, and the construction of the first turbojet engine. He had become increasingly concerned that German military aircraft were flying higher and faster than their U.S. military counterparts. One reason was the coordination of their national research efforts. Lindbergh wrote, "It is more necessary than ever before to give full scope to research if we are to regain the leadership we have lost in some of the fields of military aviation." Written just weeks after the terrifying Kristallnacht attacks in Germany shook the U.S. from its complacency, Lindbergh's letters became a key factor in the decision to create a state-of-the-art aircraft engine research laboratory in Cleveland, Ohio. The National Advisory Committee for Aeronautics, or NACA, was founded by Congress in 1915 to help the U.S. compete with Europe in the area of aeronautical technology during World War I. The NACA was a precursor of the National Aeronautics and Space Administration, or NASA, of today. As the threat of World War II loomed, the NACA expanded its research and opened 2 new laboratories. The one dedicated to the study of engines was located in Cleveland, Ohio. This Aircraft Engine Research Laboratory, or AERL, included the nation's first wind tunnel for studying actual aircraft engines in the same conditions they would experience during flight. The Altitude Wind Tunnel, or AWT, allowed researchers to systematically study aircraft engine behavior and perfect new innovations in aeronautics. Designed by some of the best and brightest minds of the day, the AWT proved itself to be a crucial and versatile testing facility, from supporting the development of the jet engine during the 1940s and 50s to its rebirth in the 1960s for Project Mercury and Centaur rocket testing.
The AWT was a huge project. This was, as you can see, it's a massive, massive structure. And there was no technology that would tell you how to build something like this. It was all new.
The Altitude Wind Tunnel was likely the most advanced wind tunnel of its time. Designed by engineers at NACA's Langley and Ames laboratories, the AWT included a number of ingenious features needed to test full-scale aircraft engines in the airspeed, altitude, and air quality experienced during flight.
This facility had to get temperatures that were very, very cold, and the air had to be almost a vacuum. And this was very difficult to do in a structure this size. And the amazing thing is it all worked perfectly.
The wind stream of the AWT was created by a massive 31-foot propeller, resulting in air speeds that could reach 500 miles per hour. As the wind stream raced down the tunnel, turning vanes directed it around the corners and straightened the flow. A powerful refrigeration system reduced the temperature to minus 47 degrees. Large exhausters in the exhauster building removed air from inside the tunnel to simulate the thin atmosphere found at high altitudes. Just prior to reaching the test section, the diameter of the tunnel decreased in order to further increase the speed of the Arctic wind stream as it rushed into the 20-foot diameter test section. The roaring engine in the test section was operated remotely from the soundproof control room, as myriad instrumentation recorded tunnel conditions and engine performance. Engine contaminants were exhausted from the tunnel through a large air scoop located just beyond the test section. Fresh air was introduced into the wind stream prior to the test section to make up for this exhausted air. One of the most daunting engineering tasks in the design of the AWT was the creation of a system to reduce the air temperature to frigid temperatures encountered in altitude conditions. This powerful system had to cool millions of cubic feet of airflow every minute, an unprecedented requirement that caught the attention of the one man considered to be a world expert on the cooling of air, Willis Carrier. Willis Carrier had pioneered the field of air conditioning and felt his company's heat transfer experts should be designing the AWT system. He informed the NACA that the Langley boys conducting the tests did not know what it was all about, and that too much money, and of more importance, too much time had been wasted already. Carrier and his engineers went on to devise the AWT cooling system, the largest of its kind in the world. In fact, it was claimed that if the massive cooling system were used for other purposes, it could generate 10,000 tons of ice per day. Willis Carrier would one day refer to the AWT as his greatest achievement. Construction of the AWT had begun as the U.S. entered World War II. There was considerable pressure to complete the construction quickly in order to aid the war effort. The new B-29 Superfortress in particular was suffering problems with its engines as it attempted to reach a 30,000-foot cruising altitude. The AWT had been designed to resolve just such an issue. On May 17th of 1943, the Memphis Belle became the first heavy bomber in World War II to successfully complete 25 bombing missions. Within 2 months, the Memphis Belle and her crew were back in the U.S. and visiting the AERL as part of a publicity tour. In the hangar behind the bomber, the large fan for the AWT was being assembled. By 1944, construction was completed and the AWT opened its doors for business. Standing inside a wind tunnel, it is easy to lose one's sense of perspective. Inside, all lines converge toward a single amorphous vanishing point, a virtual light at the end of the tunnel. In order to gain some perspective on the true dimensions of the tunnel, it is helpful to bring a person into view. In much the same way, the research conducted at the AWT and the scope of its changing mission can be best put into perspective by bringing a different individual into frame, Dr. Abe Silverstein. Dr. Abe Silverstein is best known as one of NASA's founding fathers and is credited with having named the Mercury and Apollo programs. He began his career in 1929 as an NACA researcher at Langley's massive full-scale wind tunnel. In 1943, he was transferred to Cleveland to manage the newly constructed altitude wind tunnel. He immediately set to work, assembling a 90-person team to run the tunnel. Many had been involved in its design and construction. Behind the scenes, Silverstein was involved in something far more secretive. The nation's first turbojet engine. The jet engine was developed independently in both Germany and Great Britain during the 1930s. American military leaders had witnessed the first British test flight of the engine in 1941. Plans for the engine were soon secretly transferred to the U.S., where General Electric, or GE, assembled it to create the IA engine, which was almost immediately upgraded and renamed the I-16. The I-16 was incorporated into a Bell YP-59A Aerocomet airframe. In 1943, GE summoned Abe Silverstein to its West Lynn facility to discuss testing the I-16 in altitude conditions. When later asked why he was selected to participate in the secret project, Silverstein replied, "We had the only altitude tunnel. That's the reason I went." Soon afterward, one of the jets was flown to Cleveland for testing in the AWT. Modifications based on the AWT studies allowed better distribution of airflow and reduced drag, improving the aircraft's performance by 25%. However, the Era comet would not play a role in World War II. The tests would portend an entire new role for the AWT, the development of the turbojet. In May 1944, an engine from the Boeing B-29 Superfortress was finally installed in the AWT. Researchers determined that its cooling problems stemmed from inconsistent fuel mixtures and poor airflow. By devising a fuel injection system and redirecting the airflow through the engine cylinders, they were able to improve the fuel efficiency by 18%, thus broadening the B-29's flight range and increasing its armament capabilities. The results were too late, however. The B-29's original strategy of high-altitude precision bombing of Japan had been changed to low-altitude firebombing, and the NACA's improvements were not implemented until after the war. The Lockheed YP-80A Shooting Star was the first jet aircraft to be completely manufactured in the U.S., and the first U.S. aircraft to ever fly faster than 500 miles per hour. Studies on the engine at the AWT resulted in the restarting of its GE I-40 engine above 20,000 feet for the first time, and an almost instantaneous 50% increase in thrust through use of a variable area nozzle. The Shooting Star would later go on to a successful reincarnation as the Lockheed F-80 during the Korean War. In the end, the AWT had little effect on the outcome of the war. Its most applicable contribution, the baffling of the B-29 engines, was not implemented until later. Although U.S. development of the turbojet would not be fast enough to make any significant impact on the outcome of the war, it did have long-term effects. The AWT demonstrated remarkable flexibility and became a significant contributor in developing the nation's first jet engines, both centrifugal and axial flow. The AWT had not only survived the turbojet revolution, it had embraced it. During its first 18 months of service, the tunnel was modified to test jet engines. The staff showed that it could handle the new facility. A methodology of analysis was established that would be applied repeatedly over the next decade, and the emerging AERL leadership showed that it could change course with almost no warning. The end of World War II brought about a reorganization of the entire laboratory. Turbojet research and the new realm of high-speed flight became the top priorities. Abe Silverstein was promoted to Chief of the Wind Tunnels and Flight Division, and in 1949 became Director of Research for the entire laboratory. One of the most significant problems with the early turbojets was combustion at high altitudes. The AWT was the nation's only facility in which the combustion and performance characteristics of a turbojet could be studied under altitude conditions. Nearly every U.S. jet engine model in the 1940s was tested in the AWT.
The engine companies would send their engines here, and they would be just put through their paces. And a great deal of marvelous data was then able to be released to the engine companies.
Components such as the variable area nozzle and afterburner were run successfully for the first time in the AWT.
The afterburner was actually developed at NASA Lewis, and there's a story about Abe Silverstein, who is Director of Research, who peeked in the window and saw the plume of fire coming out of that afterburner, and he was thrilled because it was the first time that it had been tested.
As the 1940s drew to a close, the AWT completed its first sprint. The tunnel had been in almost constant operation for 6 years. It had played an important role in the steady development of the jet engine and was used to study ramjets and turboprops. The study and improvement of the axial flow engine from 1945 to 1949 was the AWT's most enduring contribution to the aerospace field.
The axial flow compressor was really the great contribution that this center made to the development of jet engines. The United States was really a pioneer in the development of the axial compressor. Although they'd been used in Europe, they weren't perfected until Lewis Research Center got their hands on it.
The improvements developed in the 1940s would manifest themselves with drastic increases in engine performance and thrust in the early 1950s. In 1952, the AWT underwent an overhaul to increase its testing abilities. A new fan, exhausters, exhaust cooler, and water pump system were added. Afterwards, a series of larger engines were tested in the tunnel. Pratt & Whitney's J57 engine was probably the most successful jet engine of this period. The AWT conducted both general engine studies and a year-long noise suppression investigation on the J57. By the late 1950s, however, use of the subsonic AWT began declining, and NACA aircraft engine research began plateauing. Some engineers were wondering, where do we go from here? The answer came on October 4th, 1957, with the launch of Sputnik and the laboratory's integration with the new NASA space agency 1 year later. Silverstein had been summoned to Washington, D.C. to help create and lead the new agency. The NACA Aircraft Engine Research Facility was renamed NASA Lewis Research Center. The AWT would play a significant role in NASA's first effort, Project Mercury, only not as a wind tunnel.
The agency began to recognize that at some point all these aeronautical capabilities had application for advancing the technologies that we need to do space travel and space exploration. AWT was one of the prime examples.
The refrigeration coils and turning vanes were removed from the western leg of the tunnel so that the Big Joe attitude control and retro rocket system could be tested at simulated altitudes up to 80,000 feet. Big Joe was a successful single attempt early in Project Mercury to use a full-scale Atlas booster and test the re-entry of a boilerplate Mercury capsule without actually placing it in orbit. Lewis designed the attitude control system and assembled the components. Its guidance system was tested in the AWT. Mercury capsule testing in the AWT continued afterwards with the separation system for the Atlas and Redstone boosters, retro rockets calibration, and escape tower rockets. Perhaps the best-known AWT studies, however, were conducted in the gimbal rig. A gimbling platform had been set up in the AWT for the Big Joe tests. Afterwards, a pilot's chair, Mach control panel, and nitrogen jet control system were added to the rig. The Mercury astronauts would use this multi-axis spin test inertial facility, or MASTIF, to practice bringing a tumbling spacecraft under control. A crude dressing room known as the Astro Penthouse was temporarily constructed in the AWT with a cot for astronauts to recuperate on after their rides. In early 1960, the 7 astronauts, a female astronaut trainee, and several pilots traveled to Lewis to train on the MASTIF. Alan Shepard would be first. On the initial runs, Shepard did well, bringing the machine under control on 1 and 2 axes. Once all 3 axes were in motion, however, Shepard became ill and had to activate the chicken switch that signaled to the engineers to shut down the machine. Over the next few days, however, Shepard continued to climb into the rig until he developed a method to bring the machine to a standstill. John Glenn, Gus Grissom, and the others followed suit. When the AWT had come online just 15 years before, no one could have foreseen that it would be used as an altitude tank for manned space missions. But once again, it and its staff adapted quickly and contributed to a new role.
Out of the test cells, these wonderful mechanics and technicians came and switched their attention from airplane problems to space problems, we found that transition was almost seamless.
The Big Joe capsule verified that the autopilot could keep the heat shield in position during re-entry. The Mercury escape system was never deployed during an actual launch. But the tumbling capsule scenario did manifest itself on Neil Armstrong and Dave Scott's Gemini 8 mission. Following the decision to attempt to go to the moon, NASA began rapidly expanding its staff and test facilities.
The space effort is extremely interesting, and it is an area in which there will be considerable growth for the future. I think the young men in this country who have been properly trained in the sciences and technology are, in many cases, eager to get into the program, and this will afford them the opportunity.
Well, the beauty of government facilities is that they can be adapted to a variety of uses, and it's not really the facilities, but the people who are so creative and able to do this, and they were able to find new uses for old structures.
One capability considered necessary by Lewis was a large space simulation chamber. Initial space flights revealed that the behavior of engines, operating systems, and flight hardware were affected by the environmental conditions encountered in space. It was decided to construct 2 test chambers within the AWT's tunnel shell, one capable of simulating the altitudes of outer space, the other of Earth's upper atmosphere. Bulkheads were placed within the tunnel to seal off the new chambers. The exterior shell of the east end was rewelded and a vacuum pump house was built underneath. After over a year of construction, the facility was officially renamed the Space Power Chambers, or SPC, on September 12, 1962. Its mission, however, would change dramatically just weeks later. Centaur was a powerful second-stage rocket designed by General Dynamics to run on liquid hydrogen and oxygen. It had a sophisticated design that allowed it to carry larger payloads and restart its engines in space. NASA was relying on the new rocket to send a series of the Surveyor spacecraft to the moon to photograph and sample the lunar surface as a precursor to the Apollo landings.
We didn't know a lot about the moon, so programs like Lunar Orbiter were designed to find out things that were important to the design of the Apollo lander and, in fact, the entire Apollo system.
After its initial launch exploded 49 seconds into the mission, the program was transferred to Lewis. Silverstein returned to Cleveland as Center Director in 1961 and personally oversaw the Centaur work. After a year of modifications and testing at Lewis's other facilities, the second Centaur launch was successful.
It was a very exciting time. We were working on a high-priority program, had the highest national priority. It was a precursor to Apollo. Apollo was not going to happen without our perfecting the Centaur, so the Centaur could complete the Surveyor program.
The first study in SPC's high-altitude chamber analyzed the retro rockets, which separated the Centaur from the Atlas booster. A model that recreated the mass properties of a full-size Atlas Centaur was hung horizontally on a trolley system. These tests would result in a new jettison method that significantly reduced the separation time and thus minimized the danger of collision between the 2 stages during separation. A number of modifications were made to the SPC vacuum tank to accommodate a full-scale Centaur, the most prominent of which was the addition of a cylindrical extension with a detachable dome so that the rocket could be positioned vertically. A complex setup was installed inside the chamber to replicate other aspects of outer space. A liquid nitrogen-filled cold wall enveloped the Centaur to simulate the cryogenic temperatures of space. Solar radiation was replicated using 6 banks of quartz lamps. Exhausters below the chamber created pressure levels found at an altitude of 100 miles. Electronic malfunctions were the most likely cause of failures in space.
Silverstein doctrine said that anything that can be tested meaningfully on the ground before flight will be. That is to say, conditions can be simulated accurately enough that you can do a meaningful test. We had to construct an entire control room that looked very much, if not almost identical, with the control room to be found at the launch complex at Cape Kennedy, had to be duplicated here. That's how you run the systems on the Centaur.
In October 1963, a Centaur rocket was flown to Cleveland for the tests.
And that Centaur was brought from the Cape here to Cleveland. I was here the day it arrived, I'll never forget it, and was set into the chamber in a vertical state on a stand.
Long soaks inside SPC's vacuum tank would help the Lewis team determine the effects of the space environment on Centaur's electronics. For several months, General Dynamics personnel worked with Lewis researchers as they studied and began reassembling the rocket in the shop area.
Well, our engineers and mechanics and technicians who had never before been exposed to a machine like the Centaur had to become educated about what it is and how you handle it, especially this fragile, thin-walled structure that you had to be very careful handling because it could not sustain its own weight.
The effect of heat, both on the electronics and emanating from the electronics, was one of the primary concerns going into the Centaur tests. The liquid hydrogen propellant had an extremely low boiling point, so any additional heat could cause problems.
We had to have step-by-step procedures that were carefully controlled, changes were controlled. We were all on headsets, would sit at our consoles and operate our systems. I had the range safety control, C-band telemetry systems under my responsibility. And we ran through our procedures under the control of a test conductor, and it would take the better part of a day to get through a number of runs.
The SPC tests, which replicated the entire mission except the firing of the engines, determined that the electronics did not transfer heat to the spacecraft or propellant tanks.
So that testing was done here, and it was a major step forward in increasing the reliability of the Atlas Centaur.
The June 30th, 1964 launch of Atlas Centaur 3 was successful, but the rocket's guidance computer had been interrupted briefly during the ejection of the nose fairing. This mishap could result in a future launch failure. Nose fairings provided an aerodynamic shield for the payload, guidance system, and electronics package as the rocket travels through the Earth's atmosphere. Upon entering space, the two pieces are ejected away from the space vehicle.
The trick is to get those shrouds, after the appropriate period of time in flight, those shrouds separated and safely so that they don't damage the rocket, they don't damage the spacecraft, but they do come off.
Within a month of the AC-3 incident, the jettison system was modified and shroud requalified in the SPC. The next launch was the first Centaur mission to have a completely error-free shroud jettison. The following launch attempt, Atlas Centaur 5, never escaped the pad, however. An ensuing redesign required a retesting of the shroud and SPC.
We did many tests of Centaur shrouds on both ends, beginning with the Surveyor, the first payload carried by Centaur, and later into larger shrouds that involved orbiting astronomical observatories. It was done on the other end of this chamber.
Atlas Centaur 6 launched from Cape Canaveral on August 11, 1965, successfully placed a Surveyor model into an elliptical Earth orbit. The mission restored the nation's confidence in the Centaur's capabilities. Finally, on May 30, 1966, the Atlas Centaur 10 vehicle lifted off from Cape Canaveral carrying the Surveyor 1 spacecraft. The Centaur stage performed perfectly, and Surveyor was on its way. 3 days later, the Surveyor began sending back images from the surface of the moon. The problematic Centaur had been turned into a tremendous success, thanks in part to the testing at the SPC. 4 years of intense work at the center had paid off. A series of satellites carrying large telescopes in the late 1960s and early 1970s were designed to view distant stars and galaxies. The high-altitude SPC chamber was used to test the shroud separation systems for most of these missions. The second of these, launched in 1968, was the largest payload ever carried by a Centaur. After only a month, the satellite obtained over 20 times more ultraviolet data from stars than all of the sounding rocket studies of the previous 15 years combined. The next mission, however, failed when one of the bolts securing the shroud did not release. The SPC was used for the failure investigation and testing of the new single-motion design. SPC continued these large shroud jettison tests for additional missions until 1975. The SPC had proven its value during the extensive Centaur testing of the 1960s. However, newer, more powerful facilities began to supersede its abilities. By the mid-1970s, the space power chamber was shut down. Usable equipment was removed. Doors were shut. The electrical connections severed. And the light at the end of the tunnel went dark. Over the coming years, the shop area was repurposed for work on electric vehicles and eventually became a successful antenna testing facility. In 1985, an extensive effort was made to study a proposal to restore the AWT wind tunnel for vertical and/or short takeoff and landing, or VSTOL, high-speed turboprop, and rotocraft testing. When Congress canceled the proposed restoration, the tunnel slipped into a deep hibernation. Though the steel behemoth would continue to stand, the rust was slowly beginning to show. The stories of the altitude wind tunnel and space power chambers were fading, along with the men and women who had once brought the facilities to thundering life. The once thriving facility would remain inky black and dead quiet for 25 years. In December of 2008, there was a clamoring on the outside tunnel wall. After a few minutes, molten steel began to drip to the tunnel floor. The tunnel had been built to resist the forces of high-speed winds and a crushing vacuum environment. However, it was no match for the blazing hot knife of a cutting torch. The AWT and SPC were coming down. In 2004, NASA headquarters had offered its center's funds to demolish unused structures. The NASA Center in Cleveland, which had been renamed the Glenn Research Center, decided it was time to remove the AWT and SPC. NASA Glenn spent 3 years photographing, researching, and documenting the history of the AWT before its demolition. The AWT SPC facility was one of the most successful test facilities for both the NACA and NASA. And yet, the true strength of the AWT SPC facility cannot be measured in terms of steel and wind speed. For the building itself would be of minimal benefit, were it not for the excellence of its staff and far-sighted leadership, as exemplified by Dr. Abe Silverstein. the tunnel is now gone. The echoes of its highly skilled staff and the advancements they made live on.